In this video we discuss this ordinary differential equation, and this ordinary differential equation is responsible for modeling population. So you have the derivative of p with respect to time, p is the population, equals a constant times the population. So the rate of change of the population is proportional to this product. So the rate of change is proportional to the population. T is time and R is a strictly positive constant. And this is the initial condition. So for t equals 0, then we have a value p0, which satisfies this initial condition. What we would like to do is to write the solution of this ODE, of this initial problem, to write the solution in closed form. Again, this initial value problem is a preliminary model for modeling population. There are more sophisticated models, but this is the simplest one I can produce. So let's take the differential equation dp over dt equals r times p. Now from here we can write dp over p equals r times dt. This is a very convenient ordinary differential equation. I'm doing separation. I separate the variables. I'm doing separation of variables. So here I integrate. I have dp over p equals the integral r dt plus the natural logarithm of c. So this is the constant that comes from doing the integration. So this is natural logarithm of p equals r times t plus natural logarithm of c. I take the natural logarithm of c at the left hand side. So now from the properties of the natural logarithm, this is p over c equals r times t. Now we know that the exponential function and the natural logarithm are inverse functions. So I write it in this way. And from here I have p over c equals e to the power of r times t. So p equals c times e. So this is my general solution, where c is a real coefficient and can be specified from initial condition. So I rewrite the function is p of t equals c times e to the power of r times t. For t equals 0, p of 0 is c times e to the power of r times 0. So this is c and this is p0. So the constant c is p0. As a consequence, My solution in closed form is p of t equals p of 0 times e to the power r times t. So this is my function for the population. I can check that if somebody is unsure that this function is not correct, you should check that this function satisfies the differential equation and the initial condition. So I take the derivative of the function with respect to time. So I differentiate. P0 is just a constant. So I have derivative with respect to time of the exponential function. So this is P0 times R times e to the power of r times t. So this is r times p0 times e to the power of r times t. So this part is p, r times p. So I obtain that dp over dt is r times p. So this is satisfied, and I check p0. P evaluated at 0 is p0 times e to the power of r times 0. So this is p0. So this function is the population depending on time. And of course, this model is problematic because if you take t to go to infinity, then you have the limit of this function. Of course, you have the exponential for t going to infinity. This goes to infinity. So from here, we can deduce that this is not a very sufficient model in order to model the population, because for increasing t, this whole thing blows up. There is a more sophisticated equation, ordinary differential equation, which includes some further parameters. I hope that you have enjoyed this video, and until the next time, all the best.